Welcome to the course on FPGA based signal processing systems. In continuation with the sequential logic circuits, the merely and more machines, this finite state machines we had learned. We will be doing the sequence detector, which is also part of the finite state machines in this lecture. So, the state machine, for example, on seeing this is a representation of the merely state machine, in which there are A, B, C, D. There are 4 states, and the inputs for the given inputs, what is the input and output representations are mentioned in the diagram. So, suppose for example, in state A, the input is 1 and output is 0. On state A, staying in the same state. If in state A, if you receive 0, then move to the next state B and the output is 0. In state B, again stay in the state if the input is 0. So, that means we have in the first state A, we see that 1, you stay in that state, do not move to the next state. So, and move to the next state only if it's 0 is received. Okay. And if you receive 0 again here, then do not move. So, move only to the next state when 1 is received. At C, again move to the next state only if 0 is received. If 1 is received, go back and stay over in the state A. Okay. So, this is this 1 0. At D, again we will look see that this can be, if you get to 1, then move to next state. Okay, and give the output as 1. So, this is the code which actually, if we say in the sequence, it is detecting 0 1 0 1. So, we can say this is the detector of 0 1 0 1. So, the sequence detector can be of 2 types. One is overlapping sequence detector or non-overlapping sequence detector. So, the sequence of numbers which has come, we try to identify a certain pattern, for example 0 1 0 1 here. So, once this is 0 1 1, it is in state C, and again it looks for whether in state C, if you get 0 again, go to D. Okay, 0 again, go to D, and D you get 1, so fulfill that 1. So, it's clearly the overlapping case. So, 0 1 0 1, this is the first part identified, the output will be 1, and then this 0 where you are, which again if you receive 0, that is a part of 0 1, another 0 1 0 1. So, here again we get 1 output. Okay. So, in this case, this is a overlapping case of state machine, merely state machine, of course. It is detecting a sequence 0 1 0 1. So, if not at this stage, if not you are not receiving the 0 next, if you are receiving 1, that means 0 1 0 1, and then next bit is 1, then go back and stay over the state where you are. So, it is not going to form any of the input bit which we are expecting. Okay. So, go and start over again from A in this case. Okay. Similarly, at suppose 0 1 0 received, 1 received, the expected 1, and then again here 0 received. If you receive 1, okay, you are on track, then the expected sequence is detected. If not, that is, if you receive again 0, then this is not going to form a sequence which is expected. Okay. So, go back and stay over here, that is 0, you may get 1 again 0 1, or you may get 0 0, then stay in that state only. So, it's 0 0. Okay. So, this is the case of intermediate if you are not on the track. So, in the design of this circuit, one way is design this sequence detector of a sequential circuit, or we would, given the state diagram, get the digital equivalent, digital circuit equivalent of it. So, in the previous examples and the Verilog module, what we have developed is that digital circuits have been given in the state machine, and we have got this state diagram for the equivalent of that digital circuit. Here, the example of the given the state diagram, what is going to be the digital circuit. Okay. anyway, to write the Verilog module for the state machine, it is sufficient to have this state diagram. If once you have the state diagram, you simply follow the state transition table, form a state transition table, and then get the code done. Okay, so you have this input and the output and the next state is the current state, everything in this. So 3 always block as far as we have learned. So the module can be log module can be developed. So, so this is the just an example which can, if you have the state diagram for the, that is make a state diagram for this sequence detector 0101. So this how do we first make it this for the detector, sequence detector, what is the state diagram, to how to develop it, the meaning. First expecting that 0101, the number of bits or pattern you want to identify decides the number of states. So here 4 bits, so A, B, C, D, 4 states are required. Okay, so that, and then first state, suppose it can be any number A, B, C, D or P, Q, R, S, T or anything. So A, in this A, if we have first expected bit is 0. Okay, so first if you suppose if you get, first go on a track assuming that more optimistically, first if in the state A, yes, I received 0, so then move to next state, that is I received a 0 and go to the next state. This is the first one, first diagram we have to make, this state A and go to the next state. Okay, so if I receive 0, so this 0, but still I have not completed the detection, so the output is 0. At B, again expected one is bit is 1. So if I receive 1, so go to the next state, receive enable input 1 and output is still 0, go to next state C. So this path is the next one should be drawn. Then after this at C, yes, if I get, I am going to get a very optimistically that next bit is 0. So if I get 0, then output is 0, go to the next state D. So at D again, if I get 1, yes, if it is not a overlapping case, then go back to A and start over again. Okay, so that is 0101 for non-overlapping. Yes, if it is going to be overlapping, still you have done, we have to check A, B, C and the previous states where which if it is pointed, so that it can be part of the sequence. Okay, so in this 0101 here, if you point this 1 over here, that means you have already 01 is received. So the next state can be 0 and 1 possible. So that's why it is given to in this C, pointed to C. So if because of the overlapping case. So, and then after making this correct sequence of inputs which has been received, if not, the breaking sequence needs to be added in the state diagram. So once we have A, B, C, D, these 4 and getting this D to C. Okay, these are the red ones marked are done now. So now check at each stage if you don't receive the expected bit. Okay, so that at A, suppose you don't receive 0, you receive 1. So stay in the same state, and because at the starting point if you receive 1 instead of 0, then you are nowhere, so stay in that same state. And then at B, come to the next state and see that is whether you are receiving the correct bit or not. At B, so if you receive 1, go to the next state, but if not, and again you have received 0, then you are receiving again 0, stay in that state, because it is not going to help in any of this, but it may be a starting point of this 0. So you stay in the state B, and then at C again the breaking sequence is 0 1 0 1 is achieved, 0 1 is achieved, then you have to get 0 here, instead of 0 you get 1. Okay, 0 1, instead of the 0 you get 1. So that's not going to form a part of the sequence which is expected. So go back to the A again, 0 1 1. Okay, so this is the case, next breaking sequence. So the first breaking sequence, second breaking sequence and the third breaking sequence, and then at C, this is breaking sequence we have done, and if you are getting, you are on the right track, go to the next one. At D again we check the breaking sequence, if you are receiving the correct bit, yes, 1, go to the overlapping sequence, this is done. If not, that means 0 1 and then 0 is received. If you receive 0 again, okay, so that may be a starting point here. So pointing this breaking sequence to this place. Okay, so instead of having it going to the start over again, it is also possible that anyway the state diagram is not unique. You can have the different more state diagrams for the same sequence detector. So this A, which can be pointed out to A as well, D to this. So this is the part. Now the getting after doing this, so the first step is that for the sequence detector or the expected sequence, decide the number of states, that is 4 states here, 4 bits, 4 states. And the second point is, if you are in the right track, A, B, C, D, that form that path, and then decide the breaking sequence for each state. That is, if I did not receive or the bit which is expected, where should then the state should go. Okay, so those details can be made at every stage, every state. Okay, so that is the completion of, gives the completion of the state diagram. So now the suppose we get the input sequence like this. Okay, so I am starting from here, that is not from left hand side. 0 is received, 0 1 1 0 1 0 1. Okay, so the output should be whether I found the sequence or not. Okay, so the output at this stage, it is 0, the 0 and 0, here it is 1. So at this bit, once it is received, it should give the 1 here. Okay, so after that, 0 again received, 1 received. So is it, this is the first pattern, and the next pattern is the 0 1 0 1. So give the output as 1, and then 0 0 1. So this is not going to form, or this 4 is not going to form the pattern which is expected. So finally here this pattern is getting complete, 0 1 0 1. So this gives the output 1. So the output will be, when found is 1, that means the pattern which is expected is found, then the output is 1. Okay, in this. So you have to make the Verilog module in which that this state, using the state diagram. What is the always for state memory, like in the previous state machines, and the next state logic, which comprises of all these details. After getting the next state logic, and the output should be, even it can be incorporated in the next state logic itself, or output case, if what is the state at which the output is received. If D equal to this and 1, the output is going to be 1. So the output logic contains this information. Okay, so in the Verilog module, we'll be doing that I'll show you the code and its output. So this is one X01 and 01 detector, which has the 4-bit sequence detector, has the 4 states. And how, let us see this state diagram, how can we convert into digital circuit. Okay, so first step is to have the state transition table from the state diagram. Okay, the state diagram which we have here, and the state table we obtained from the state diagram. Okay, so usually we do in the previous case that we had done the state transition table, and from that we have drawn the state diagram. Here is the reverse one. So Q1 Q0, we have the 4 states, we know that here. So Q0 and Q1 is the 2 bits A B C D, and Q1 star and Q0 star comma Z, because it's a Mealy machine which is giving the next states Q1 star and Q0 star and Z. The input, of course, this has an input sequence of input as going to arrive to in the sequence detector to find out the pattern. Here is x equal to 0, so the input is 0. If we are in the present state A, x equal to 0, go to state B. This is over here, this is given here, and output is 0. Okay, so still we have not achieved this, output is 0. And at state B, if the input is the enable input is 0, then output is 0 here, stay over state. At C, the input is, the x input is 0, go to D. This is D, and output is 0. At D, the input is 0, go to B, from here. If enable is 1, similarly this case, this case, and this case, and this case would be giving the state transition table. So along with that we can get the outputs as well. Okay, so this is the state table which had been we had obtained from the state diagram given. So from this we can have the name from the alphabets. We used to jump from this state to this in the previous examples. Now going back from here to here. Okay, so this ABCD can be assigned any 2 bits. Okay, here Q0 and Q1. So A is assigned 00, B is 01, and C 10, and D is 11. Okay, Q0 and Q1. So this can be anything. D can be 00, C can be 11, B can be of 10, and so on. So just to follow the order 2 bits, so ABCD, it is given ABCD. So these ABCDs change it to codes, 2-bit codes, that here 2 bits. B is 01, this is 01, and D, and this is B here, and all this A are 00. C is again change them in the next table. So we got this table x0 and x1, the state from the diagram we got this state transition, and then assign the codes for it and get the Karnaugh map for each output for the Z and Q1 star and Q0 star. Okay, so for the inputs, what are the inputs to the Karnaugh map? When x is 0 and present state, when x is 1, what are the present states? Get the Q1 star and Q0 star output, what is the expression, and similarly for output also. So let's see the Karnaugh maps changed. Yeah, we got it here. So for the output first is the, okay, the Karnaugh map is that x is x0 or 1, yes, x0 or 1, and Q0 and Q1 we have taken it in this in the Karnaugh map. And you see the output only x0, all the outputs are 0, x1, all the outputs are 0 only. At this point this is 1, so we have all the table values 0 and 1. So it would give z, the expression is going to be x q1 q0, huh? So just a multiplication of input and the current states. So for q1 star, similarly if we get this q1 star is this 1 0 0 0, these are the next states. Okay, going to be filled up. So you have 1 1 1 here with x equal to 0 there are 1 1, and when x equal to 1 there are 2 1s. Okay, so q1 star, so the expression we will be getting from this here x1 q0. Okay, so x1 and q0. So from here similarly the other one q0 star has if you get the Karnaugh map or q0 star, there are 4 1s for x equal to 0 and others are 0. So you get x dash or x dash itself. So x q1 and q0 is for this expression z, and q1 star is here x q0, and there is one more 1 here, that is x dash q1 q0 dash. So this is contributing the second equation for q1 star, and q0 star here the next state is simply x dash. So obtaining this equation, now we can draw the circuit for it. So the q0 star and q1 q0 star is going to be using the D flip flop. So this would change if there is if the flip flop used will be different. So for the D flip flop, D1 and D0 is the characteristic equation for this. So now getting them in the circuit. So this is the circuit. So we have this x and 2 flip flop, which is the state memory. You can see the state memory from the equation only this circuit is drawn. So state memory and the output logic. So here is the next state logic. The other thing, the total portion is giving the next state logic. So here, if you see that q naught star over here, which is x dash itself, so this is going to be simply x dash, which is d naught. Q naught star is d naught, so you get this simply x dash, and q1 is d1, so which is giving the x q naught, this one, and x dash q1 q naught dash is this, or them give it to d1. So the two flip flop, and the output is that is x q naught and q1. You can notice that this is the current states deciding the output, as well as the x, the input which is coming from here giving the AND gate. So here is the x also decides the output logic. So this is a Mealy machine which we have started with. You can see that state diagram was a Mealy machine, and from that Mealy machine we got this circuit. So if you are given with this circuit, you know how to go to the how to get the state diagram, and if the state diagram is given, you know how to get this digital circuits through this example. So next state logic, state memory, and the output logic, three of them can be distinguished, and it is a Mealy state machine. So with that example, so the sequence detector, we have this, suppose you want to detect this sequence as 100. Okay, so how do we decide the states? It is 3 states, ABC, and if first state A, and then if you receive, let us see that here, okay, maybe the ABC, the states A, B and C. First we need to check the make the diagram for A. At A, if you receive 1, the expected value go to B, that is okay, and output is 0. At B, so this path is formed first, and then what is the input you are getting, that is B. At B, if you get 0, yeah, you are in the right track, then go to C, that is 1 0 is received, 1 is received, 0 is received. And then yes, again in C, if you receive 0, good, and the output is 1, go to A. Okay, so this is not a overlapping case. Okay, so if this is the ABC, suppose 1 you receive 0, in the, now we have to add the breaking sequence, right? So the correct track ones are marked over here. So if at A, instead of 1 I receive 0, what should I do? Stay in that state, and output is 0 here still, because you are receiving 0, that is not going to form a part of a sequence or anything, so it is better to stay over there at A. At B, again find the breaking sequence, you are here 1, and after that you are expecting 0, but you receive 1. Okay, so 1, this is not in the part of the sequence, so this stay over here, so at least it can be starting point of 1. Okay, so stay over here B, the what if you receive 1. At C, again you are 1 0 expecting 0, if not you are getting 1. Okay, so in that case go to B and stay over there, because this may be a starting point of 1 0 0. So if you add this, it makes the state diagram overlapping. So 1 1 0, then you go to here 1, okay, and then expecting this, so 1, this can be a 1 or 1, which we have got it from here, or we can get it from 1 here. Okay, so this, if you are from A, you can come to B, or from C also you can come to B 1, and then expect 0, or in this state again if you receive 1, that's not going to be a part of this, stay over there, okay, at 1 only. Okay, and expect this 0. So the breaking sequence is 1 here, 2, and the third one is this. We can go, instead of going to the A after receiving 1 0, it is not advisable to go to A and start over again, because you are partly right, 1 0 is already received in the from the pattern expected. So we need only one bit, so intermediate step is preferable in this case. You can see 1 0 1 0 0, and get back to A here. So you can notice so tracking the correct sequence in the diagram, also the breaking sequence is necessary to put at the each state. Okay, so when we identify, it's easy to get the ABC for the correct pattern, whereas deciding the breaking sequence, breaking of sequence. If it is not received, suppose, whether we have to stay in that state or going to the next any intermediate state where it can form a part of a sequence, or partly the sequence is already identified from that point. Here it's a perfect example for one. It's going to staying here 1 and then expecting 0 0, this because this is 1. Okay. So one more thing we can notice in this part is that reset. Okay. So if you have the separate reset in the Verilog module, which can help in the state machine to to stop it anywhere, you can have more control over this state machine. So when we develop the state diagram, so the next state logic then and the next state logic gives these details of that, and the output logic would be appearing based on the output detected, and the logic used for this output detected. And in the case of state memory, yes, this reset needs to be the asynchronous reset. What we say that if it always at the passage of the clock or reset, if reset is 1, go to make it 0 0, or state the state is A. Else if the passage of the clock or the clock is there, then move to depends on the S next can be assigned to S reg. So we need the state memory, the change in the state memory code that always block to reset that, so that at any point of time you will not be stuck. If the state machine is not moving from one to another, you can have the reset to bring it to the initial state. Okay, so this is, we will be doing that Verilog code as well for this, and then we will include this reset in this case. This is for 100. The sequence detector of the one more, we had seen the 4-bit and then 3-bit, and then this is 5-bit 11011. Okay, so there will be 5 states, yeah, A, B, C, D, E. There are 5 states from the expected one 1 1 0 1 1 1. Okay, so we will start from here. So for 1, this is the first track, and then B to C, there is 1 0 again, and then if C to D, it is 0 here, 1 1 0. At D again, if you get 1, go to E, this is the right track. Okay, A, B, C, D, and then E. Okay, so again from E you get 1, yes, go to C and make it, the output is 1. Okay, so at this point, because 1 we go to 1 1 1 0 1 1, so you point it to C, that is where, to this point where the code is received as 1 1. Okay, so that can be a part of the next bit. If you receive suppose 0, then that can be a part of the pattern which needs to be detected. So it is pointed to the 1 to C here. Okay, so now this is the pattern which is received correctly. Okay, if not, we need to introduce the breaking sequence at each stage. So at A, expecting 1, but if receives 0, so it's not going to part of any sequence, so stay in that state, output is 0. At B, again expecting that 1, but you are receiving 0, so this is not going to be a part of any the sequence which is needed, so go back and to A. Or it is, if you stay at B, that is that is considered to be here. Why we are going back here? So if you are staying at 0, that will be 1, no, 1, and it is like in making 1, so it is better to go back to 0. Okay, so at this is the breaking sequence, this is the breaking sequence at B. So breaking sequence at A, and then at C again 1 1, the expected is 0, but you are receiving 1, so stay in that same state, because this can form a part of a sequence, because starting sequence can have 1 1 as well. So stay in that state, expect 0 to come. Okay, so that is the breaking sequence at C. Okay, at D, yes, 1 1 1 1 0 1 1 0 is received, and the expected is 1. If not, you are getting 0 here. Okay, so that is, if you receive 0, So this is not going to form a part of a sequence, go back to A. Okay, this is the breaking sequence at D. Okay, similarly at E, there each state we need to check the breaking sequence. If I did not receive the correct state, 1101 is here. Okay, so then it receiving 0, it's not going to form the part of the sequence. Okay, so go back to 0 here. This is one this is what if this is for the overlapping case. So if it is not overlapping, this can be at E after receiving 11011, so you can directly go to A and stop here and find the breaking states. Okay, sequence how to make that. So 11011, if it is not overlapping, from E directly you can go to the make it one, make it here in this 1 and 1. Okay, so that is this can be shifted to E to A as well in the non-overlapping case. This is the overlapping case. So 5 bits sequence detector. Here I have not put the reset, we can add a reset as well in the previous example. And the Verilog module will be developing for these sequence detectors and get the as it is shown in the first example, to get the digital circuit for this that can be an exercise to do the digital circuit for this particular one. So if you consider this as a state machine, and the state machine Verilog module can be developed. If we get the digital circuit equivalent of it, you can instantiate this D flip-flops and then some few logic gates of combinational circuits for next state logic and the output logic. The Verilog module can be developed in that fashion also. So that is a separate model, but we consider this as a state machine. So so the way of model developing the Verilog module could be the state memory, next state logic and output logic block with always blocks. So that is more easier than the instantiating the D flip flops and all combinational circuits and the next state logic and the output logic. But in the synthesis process, we will see the difference, how this instantiated one and the code which we had developed forming using the state machine model. Now, what is the difference in the digital circuits? That part we can explore, study more on the how these real time hardware components are realized in the state machine module, are instantiating the digital circuits. So the difference can be observed in the synthesis process when we do it in the real time or dumping this code in the FPGAs. Thank you.